Let me know if you can see it or not. Can you see my screen now?
Yes, sir.
Yes,
All
sir.
right. Okay, so we can start today's lecture. So let me recall what we did in the last class. We in the last lecture we introduced linear transformation. Then we saw some examples, and then at the end of the class we also proved rank nullity theorem and some corollaries of that result. In and then in the at the end of the lecture, I mentioned that there is a way to define arbitrary linear maps or linear transformation from a vector space to another vector space. So we'll start with that result. So let me recall what is the statement of that result. So what that result says. Okay. So it says that suppose that we have a vector space. So let V be a vector space or for the timing, let's say finite dimensional vector space, and then you tell me the infinite dimension version of this. So finite dimension vector space over F, and then W be any vector space over the same field F. Okay. And suppose that since V is a finite dimensional, assume that we have a basis for this vector space. So let's say V1, V2, and so on up to Vn. This is a basis of V. Okay. Then what you do, you choose n vectors, any n vectors, say arbitrary vectors. Let's say W1 to Wn in W. So in this set, the elements can repeat. So you can choose any n arbitrary vectors, like W1 n times you can choose the same vector. That is also fine. Okay. Then there exists a unique linear transformation from V to W such that, so linear transformation, let's say T from V to W, or let me write it in this way. So there exists a unique linear transformation T from V to W such that T of Vi is equal to Wi for all I equal to 1 to n. Okay. So what it says that if suppose you have a vector space of dimension n, you fix a basis, let's say V1 to Vn, any basis, and then you choose any n vectors in the other vector space W, and then you can always find a linear transformation from V to W such that this Vi goes to Wi for each I, and this linear transformation is unique. Okay. Now you change the set of vectors Wi's, then you will get a different linear transformation. If you choose a different basis, and then if you follow the same thing, then you will get a different. So this result gives you many ways to define linear transformations from one vector space to another vector space. Now, if suppose using this result, we can actually find linear transformation of our use. For example, suppose if I ask you, okay, let's say V and W are two vector space, and then I give you a, let's say, is a subspace also of V, let's say, and then I ask you, okay, define a linear transformation from V to W such that null space or the kernel of T is equal to that given subspace. Or similarly, I can ask you to define a linear transformation from V to W such that the range space is a given subspace of W, something like that. So using this result, we can actually find the linear transformation of our use. So here in this case, I did not assume anything on wi's. So you choose any wi's, any n vectors wi's, and you are done. And you can find this. Now, depending on your equation, you can always choose these wi's accordingly, so that it meets whatever is required for your problem. Okay. So I hope the result is clear. The proof is very straightforward. Now, can you tell me how to define? So we want a linear transformation. So we are given only vi's, these basis vectors, and these wi's. Okay. Now, can you define a linear transformation from V to W? Is there a way to define it? Your voice is not clear. So anybody else? Is there any way to define this linear transformation from V to W such that T of Vi is equal to Wi?
Sir, sir, every element of capital V vector space V can be represented in the form of linear combination of V1 to Vn.
Hmm.
Then
Okay.
sir, and sir, then for corresponding to every vector of vector V, we can get the map in terms of Wi.
Right. Right. So this is the idea. Yeah, I understand what you mean. So what he's saying that we have to define a linear transformation T from V to W. So that means we have to assign every vector in V to some value in W. Right. So he's saying that, so if you take any vector, let's say V in V, then because we know a basis for this vector space, we can express this V in terms of linear combination of basis vectors. So this V can be written as alpha Vi for some alpha scalars alpha, right? Now what he's saying that you define now, so you have to define this function from V to W, and then you have to show that this is linear. So what he's saying is that you take this V, which you actually can write in this way, alpha Vi, because every week you can write in this way, and then he's saying that you send this vector to this elements, this vector. So basically, what is the linear transformation? Linear transformation is TV, or you can write it in this way, uh, T of alpha I Vi, I equal to 1 to n equal to alpha I Wi. So this is the function. Now you can verify that this is a function. This is a well-defined function from V to W. Not only that, this is a linear transformation from V to W. So then this T is a linear transformation from V to W. This is very straightforward, so you can verify. And also, if you look at T of Vi, now what it is?
WI.
Just Wi, right?
WI.
So you know this is very easy. This is very easy to find such a map. So you can always find such a linear transformation that sends Vi to Wi for each I. But this linear transformation is unique. So how to show the uniqueness? Yeah.
सर एक कोई और लिनियर ट्रांसफॉर्मेशन टी जैसे को टी के इक्वल
Yes. So she's saying that you take another linear transformation. So suppose there is another linear transformation S from V to W that does exactly the same thing. That means such that S of Vi is equal to Wi. And now you show that this S is actually equal to T. Now you are trying to show two functions are equal. That means S is a linear transformation, T is a linear transformation. So you are trying to show that both these linear transformations are same. So how can we say that both these linear transformations are same? What we have to show in order to do that?
Sir, image of every element of domain is same.
Same, right? So we have to show that for every vector V, S of V is equal to T of V. So if I take any V in V, then I know that this V I can write as again similarly alpha I Vi for some alpha I. Now if I look at S of V, then what it is? By definition, I can write it equal to 1 to n. Since S is a linear transformation, I can take this S inside inside the summation. So it is S of Vi. Now what is S of Vi? It is alpha I Wi by definition, right? Now, but again, if you look at the definition of T, this summation alpha I Wi is actually T of V. And therefore, such a linear transformation is unique. So this way we can, so for example, now let me give you one example here. So, all right, so let us take an example first. Suppose that we have a vector space, let's say, let me give you a general example. Suppose that we have a vector space V and V of dimension. So let's say dimension 9. Okay, and then we have a, let's say we have a vector space W, which is of, let's say, dimension, let's say 8. Dimension of W is 8. Okay, and let us take a subspace, let's say subspace S1 of V. This is a subspace such that dimension of S1 is equal to, let's say, 4. Okay, now and take a subspace S2 of W. This is a subspace, and let's say its dimension is 5. Now can you define, let's say, um, a linear transformation T? Can you define a linear, let's say this dimension is also 4. Can you define a linear transformation T? So this is the question here. From V to W, first you tell me this, such that null space of T is equal to S1. So this is the first question. Now what is your answer here? If you say yes, you will have to give a transformation here. Any
Yes.
idea?
Yes, sir.
Yes.
Sir, we can define a linear transformation V to W such that null space is equals to S1. So we मतलब इस तरह से डिफाइन कर सकते हैं कि T मतलब ब्रेक कर सकते हैं उसको कि जो मतलब जो है अपना V है तो उसका जो एंड 9 डायमेंशन है और S1 का जो 4 डायमेंशन है तो बेसिस में 9 वेक्टर होंगे और 4 वेक्टर्स को मतलब W के 0 पे मैप करवा देंगे और 5 वेक्टर्स को एनी अदर वेक्टर्स पे मैप करवा देंगे.
Not very clear. So you'll tell me that how this is how you will define. So you are saying that there are 9 vectors in the basis. So 4
Yes.
vectors. Any 4 vectors you can assign to null space of T. So let's say according to you. So I know that you have some idea, but it is not clear. So you are saying that let's say V1 to Vn, V9, these are basis vectors of V, and then you are
Yes.
saying that you assign any, let's say the first 4 vectors I equal to 1 to 4, you assign to W, let's say some vector W, or you are saying null space, so you send them to 0, and the other vectors you don't send them to. So you assign some non-zero vector in W.
Yes, sir.
But then how do you ensure? So from here you can say that the null space of T will have dimension 4. That I agree. But how would you share? So what we want? We want that null space should be exactly equal to S1 here in the question. So
Sir,
this is not
जो
from here. You
एलिमेंट
cannot say that.
तो जो एलिमेंट्स
Sir, the-
S1 में है उनको हम 0 पे सेट करते हैं.
Your voice is not clear. Can you repeat, please?
S1 के बेसिस को एक्सटेंड कर
saying that कि जो वेक्टर S1 में है उसको जीरो मैप कर दिया जाए.
Yeah, your voice is not clear.
सर S1 के बेसिस
Yes, S1 के बेसिस को एक्सटेंड कर दिया जाए फिर
सर S1
Then?
का एक बेसिस होगा उसे एक्सटेंड कर देंगे S1 वाले बेसिस वाले एलिमेंट्स को 0 पे मैप कर देंगे और अदर्स को जो
Sir-
बाकी W के कोई भी वेक्टर्स
कोई भी नॉन जीरो वेक्टर.
यस
Okay, exactly. So this is the idea. So if you take any basis of V, that won't work. So what he's saying that you take a basis. So since S1 is a subspace of V of dimension 4, so we can always find a basis for S1. So let's say V1 to V4, this is a basis of S1. And now extend this basis to a basis. So that means you add, let's say V5 to V9. This is a basis of V. Now what he's saying, you send, so if you want to define now, see, we can use the previous result here. So we have a basis for V. Now we have to choose n vectors in W, right? And then we can always define such a map. Now the thing is that how to choose this Wi now. So he's saying that you send this first 4 vector to 0. That means the first, so these you can always do. And then for the other vectors V5 to V9, you send them to any non-zero vector, maybe that the same vector or any different non-zero vectors. You can do anything. So you just take, since W is of dimension 8, there is a non-zero vector. So you take any, let's say W is any non-zero vector in W, and then you choose this W5. Now you have chosen, see these 9 vectors in W. So now you know there is a map that sends Vi to Wi. So you don't have to write this way. This is just for your understanding. So you just choose in this way. If you do it in this way, then from previous result, you can always find the map T from V to W such that T of Vi equal to Wi. So what you do here, this way if you choose, then you can send the first 4 Vi's to 0 for I equal to 1, 2, 3, 4, and the rest of the Vi's, V5 to V9, you send to W, where W is a non-zero vector. So I equal to 5, 6, 7, 8, 9. Okay. Now for this kind of map, you can always define. And for this map, you can verify that null of T is equal to S1. So this is the idea. Okay. So this is the idea. You have to give actually the map. So this idea you can keep in mind. Now what would be the map? Can you tell me what would be the map? This map T from V to W. If I take any vector V, then I can always write it in this way. Then what would be the right hand side? How this map should be defined?
5 to
I
A
equal
scalar
to
combination
5
of
to
W.
9. Not all.
Sir,
This
only single W.
alpha WI. Yes.
So this is the map. You need T of Vi equal to Wi. Na? So if you just use the previous result, this is how. So this linear transformation, you don't have to prove that this is linear because of the previous result. We have already shown that such a linear transformation is linear. You also don't have to show that T of Vi equal to Wi because of the previous result. So we have already proved that result. If you just in your question, if it satisfies the criteria of that result, then you can directly use that result and you can show that this is the linear transformation that does the job. Similarly, can you define a linear transformation from V
Sir?
to W? So that, yes.
Sir, since you've taken only you've defined TVI from Y, I vary from 5 to 9, sir. Only single element W. Sir, that will be valid because we want null of T is equal to dimension of null of T is equal to 4.
Dimension of, yeah. So it's like Wi here is W actually. Okay.
Sir,
Because here
then,
we are saying,
sir, in last class we have done that dimension of V is equal to dimension of nullity of T plus rank of T.
hmm,
And sir, here rank of T is only 1.
rank of T is
1. Since we are taking only W, we are only taking one element of vector space capital W, that is W.
hmm,
Small w. So then that and that will be form a subspace which is having dimension 1.
okay.
So that will imply the nullity as a dimension 8. And we want dimension of nullity as a 4.
So you are saying that the rank nullity theorem is violating here. This is what you are saying.
Yes, sir. If we are taking only TBI is equal to W for all I 5 to 9, only single
Yes.
W, that
Yes.
then it is violating, sir.
Yes, sir.
We have
That's
to
correct.
take WI is different.
Sir, if we take T of Vi equals to Wi for I equals to 5 to 9,
Hmm.
And sir,
then
that WI should be linearly independent.
yes, sir. Then rank of T equals to 5
Yes.
and
Yes. I
nullity
understand.
4.
So yes. So I think this is true when Wi's are different.
Yes, sir.
All right. Okay. Yeah. This is the point I was missing. So thank you for that. So then let us choose. It's good that you understood this result. So let's say W1 to W5. You take in W, which are linearly independent, and then you assign it to Wi. Right. So then you can find these this linear transformation such that null space of T is equal to us. Right. Right. So let us ask the same question for the range space also. So let's say we have T from V to W. So the question is, can we find a linear transformation from V to W such that range of T is equal to S2? Now, how about this question? So, what is your answer for this?
Yes, sir. We can
तो
we
सेम
can
सर
define.
यहाँ पे टी
Sir,
Yeah,
we can
how to
define
do
such.
that? Yes.
Sir, means we will define T from V to S2, and
Hmm.
that is on 2. That will give the
That that
given
is
criteria. On
no
2.
no. So S2 is a subset of 4. S2 is of dimension 4, and W is of 8. So you need to define a linear transformation. It won't be on 2, na? So
Sir,
this linear
means
transformation will definitely.
we are
सर
taking
जो आपने
like
ऊपर करवाया है तो उसमें से टी वी आई इक्वल टू 0 कर देंगे, आई इक्वल टू 1 2 3 4 5,
Yes.
उसमें जो नल्टी हो जाएगा 5 हो जाएगा और रेंज हमारा 4 हो जाएगा.
No, but how would you start? How would you use S2 here? How would you ensure that range of T would be S2?
Sir, हम
We can analyze what the basic of S2. Then using
Your-
a rank nullity theorem, we can find the nullity. Then we can.
your voice is not clear. So how? No, not you don't have to use rank nullity at this point. You just define simply this map. So how would you define that? Just keeping in mind the previous result.
sir,
सर S2 को हम एक्सटेंड कर सकते हैं W का बेसिस बनाने के लिए.
So you are saying that first take a basis of W, S2. So
हेलो सर.
let's say W1 to W4. This is a basis for S2. And then
Yes,
extend this basis to a basis of W. So let's say W1 to W4 and W5 to W8. This is the basis of W. Now what?
तो इसको हम ऐसे
And
भी
let's
कर
say
सकते हैं ना कि सर डायमेंशन ऑफ V इक्वल टू 9 है, तो हमें पता है V
Equal to
से
0
V1
और I
V2
equal to
V9
10.
सर. हेलो सर.
yes, yes.
V1 V2 dot dot V9 is the basis of V,
Hmm.
and we define that TVI is equal to 0 from I equal to 1 2 3 4 5, and TVI equal to WI this. We know that span of T beta equal spans range space from where range of T equal to 4. Then हमने define किया TVI equal to 0 from I 1 to 5, then that will be 0, and we have only 4 elements, W6, W7, W8, W8, 9. Then we got a rank as 4.
So yeah, that's what you are trying to do here. So you have these vectors W1 to W4 for basis for S2. This is the basis of W. So I'm writing whatever you are saying. So some of you said that you take a basis of S2, then you extend this to a basis of W. That's fine. Now you're saying that you take V1 to V9. This is the basis of V. It's fine. Now, how would you assign these VIs to in WI such that range of T is equal to S2?
so we can take T of Vi is equal
The
to
TVI
W
equal to 0
for
from
I is
I
equal
goes
to
to 1 to 5.
4.
So
1 to
one
5.
of you is saying 1 to
1
4,
to 5.
1 to 5, W T of VI
So the
equal to
TVI equal to 0, 0.
0,
I goes 1 to 5.
1 to 5. Okay, then
And TVI
and
equal to WI from 6 to 9.
now is it so this using this linear transformation you cannot say that range of T is S2.
So,
Yes.
so we can
Your voice is not clear. So your voice is like annoying here because of some disturbance. So this map won't work. So what you do is that you send T of Vi equal to Wi for I equal to
1 to 4.
1 to 4. Okay, so you take T of Vi. So you take T of Vi equal to Wi. So let me Wi I equal to 1 to 4 and
T of Vi equals
Vi
to
is
0,
equals to 0 for I equals to 5 to
5
9.
to 9.
5 to 9. So this notation is actually for this 4 and 5, 6, 7, 8, 9. Now is it fine?
Yes, sir.
Yes, sir.
Okay. So this way, depending on your question, you can also, now there may be only one vector space V and there is only one subspace. So for example, let us take this question also. So let's say we have just vector space V of dimension 9, and we need to define a linear transformation T from V to V such that uh, range of T is equal to S1 and range of null of T is also equal to S1. First of all, you tell me whether such a map exists or not.
Not.
Not exist.
No,
Not, sir.
don't exist. Yeah, okay. Such a map doesn't exist. Okay. So if I say the dimension of V is 8, then
So then it will.
Then it will be.
sorry, dimension of V is 8, and what is the dimension of S1? Is 4.
4.
So then exist?
Yes, sir.
Yes, sir.
Yes.
Yeah. So
No,
then
sir.
what would you do?
Sir,
Then doesn't
but S1 is a subset
S1
of
is of
V.
dimension 4.
Acha. Sorry.
Yeah. So this also you can define. You just have to choose what you have to do here. You tell me what you have to do here.
Take a basis of S1 फिर extend करेंगे V तक, then map
So let's
define
say
करेंगे.
V1 to V4 is a basis of S1. You tell me, yeah, S1.
Yes, sir.
Then you are saying that
Uh,
basis this extend this to a
extend.
basis of
Yes, sir.
of V. Then now tell me T of Vi.
Vi equals to Vi 1 to 4.
T of Vi equal to
Vi.
T of Vi equal to 1 to 4.
Yes, sir. Vi 1 to 4. Yes, sir.
Okay. And
T of Vi equals to 0.
so is it correct?
Yes, sir.
So this is not correct. Why this is not correct? Because null space of T is not S1.
Yes, sir, it's not S1.
So then what you need to modify here?
Yes, so interchange कर दो Vi और 0. Sorry.
Yes. So you just do it this way. So you send T of Vi equal to 0 for I equal to 1 to 4, and T of Vi, and you send like 5 to 1, 6 to 2, 7 to 3, and 8 to 4. Is it okay now?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Okay. Accordingly, you can define your linear transformation also. All right. So now you know how to use this result. So depending on your question, you can always define such a linear transformation that sends certain vectors to another set of vectors. Okay, so let us move forward. So this is like we can, so far we have just defined linear transformation, but if we have two linear transformation, we can add them, we can define a scalar multiplication of a linear transformation, and this way we can do some algebra of linear transformation. For example, if suppose we have two linear transformation from V to W. Okay, by the way, before this, let me ask one question here. So here I assume that V is finite dimension. W I did not assume anything, but can we can you like tell me what would be if I want to state similar result for infinite dimension vector space also then? Okay, so this is an exercise. You think about it because we don't have much time. So exercise is, I'm writing it here. Exercise is infinite dimensional analog of this result. Okay, you think about it and then tell me. Okay, so let's talk about the algebra of linear transformation. Suppose that we have two linear transformation from V to W, then since we know that V and W are two sets, and linear transformation is a function from V to W, but in addition to that, it also satisfies these two properties of linear transformation, of being a linear transformation. So these are functions. So if I take two linear transformations, so these are functions from V to W, then I know how to add them. So their addition is defined. It is actually the usual addition of function. So basically we can add two linear transformation T plus A. So we can define this. How it would be defined? So you take any vector V and you send it to this one for any V in V. And if you take and similarly we can define scalar multiplication also, because scalar multiplication of function we know how to define. So you take any vector V and send it to alpha times T of V. Okay. So this way you can check that this T plus S, if you define it in this way, then you can verify that they are not only functions, they are also linear transformations. So this T plus S and alpha T, they also belong to this set. This you can verify. Now we have a set here, collection of all functions. We have a set here, collection of all linear transformation from V to W. We have defined an addition on that, and we have defined a scalar multiplication also on that. In fact, you can show that this set L VW is a collection of all linear transformation from V to W, together with these two operations, addition and scalar multiplication, as defined above. This form a vector space. This is form a vector space, right? Now there are two ways to check this. One is, as you know, how to check this is a vector space or not. Just check the 8 properties of vector space. What would be the other way? Can you tell me some like simpler way, or like quickly, that this is why it would be a vector space? Anyone?
इसका एक सब स्पेस बता देते
इसका
सब स्पेस बना देते हैं, और वो मतलब
इसका सब स्पेस बना देते हैं, इसको किसी का सब स्पेस बना देते हैं।
जैसे इसको किसी का सब स्पेस बता सकते हैं
सर।
हाँ, तो किसका बनाएंगे?
सर सभी फंक्शन का टी से डब्ल्यू
Function.
से एस तक
Yes.
जो सभी फंक्शन है ना।
Right, exactly. So you already know that these are functions. T and S are functions together with two conditions. So if we have like set of all functions, these are set of all functions, and then this set is sitting inside this. Now we know that if we have already seen here, if it add any two of linear transformation, it is again a linear transformation, and scalar multiplication is also again a linear transformation. So this set is closed under addition and scalar multiplication, and therefore this forms a subspace. So if you talk about collection of all functions from V to W under the two operation, addition of functions and scalar multiplication of function, this F is a vector space, and therefore this we have already seen by studying vector space. Here this is very clear that because of this is a subspace, and therefore it is a vector space. So this way is also you can show. All right. Okay, so we know we can add two functions, we can take a scalar multiplication. What else we can do with function? What else we can do?
Composition.
Composition, yeah, composition of linear transformation. All right. So how it is defined? So if suppose we have a linear transformation T from V to W, and suppose we have another linear transformation as from, let's say, W to Z, then define as composition T of V. How it is defined? You take this S of T of V for all V in V. Then you can verify that this composition is again a linear transformation from, so this would be a linear transformation from
From
V
V1
to Z,
V
V
to
V to
right?
V to Z.
V to Z, right? So you can verify this. Okay. Sometimes instead of S composition T, we usually write this as T. When we write this as T, the same notation, same thing, but a different notation. It's like a product of S and T, but it is not product. It is S composition. Okay, this is the same thing. Now, if so, let's say now let me ask this. So you can do the composition of, you can define the composition of S with T. Now, if suppose, let's say, uh, let's say, so let me write this as a note. So if V, W, and Z, these three vector spaces are same, let's say, then we can define as composition of S composition T. We can define, and we know that from above, this is a linear transformation from V to V. And similarly, T of S is also a linear transformation from V to D, from V to V, right? Okay.
Yes, sir.
Now, this way you can say that, okay, in general, in a vector space, the multiplication is not defined, right? We only have addition and scalar multiplication, but we cannot multiply two vectors, right? And
yes, sir.
elements of vector space, we call them as vectors. But here, for this set, the collection of all linear transformation, we can define a multiplication. It is actually the composition. Okay, so it is like you can talk about sort of multiplication. So this LV has a multiplication, but when we talk about multiplication, it is actually the composition. Okay, so it's a multiplication defined on it by composition. Okay, so now we have, in general, we expect that composition of S with T, I mean the multiplication of ST and TS, it should be same, right? I mean this is what we expect, but in general, for this linear transformation, T of S is not equal to, or not, TS is not equal to ST. Why it is so? Because this we can show by an example. If you like take this example, let's say you can verify this. This is a collection of all linear P of F is the collection of all polynomials over F. F is the field. Okay. Or let's say for simplicity, P or collection of all polynomials over R. Now you take this F T of Px, it sends every polynomial to this one. Just multiply x with this polynomial. Now you can verify that this T is a linear transformation. Similarly, if you look at this one, what is this? This is the derivative map. You take any polynomial here and you send it to its derivative. Then you can verify that T of TD is not equal to DT. Okay, this you can verify yourself. All right, so because of that, we can say that TS is not equal to ST in general. Now, if suppose, so this is true for any two functions from V to V, any two linear transformation here, whatever I said. But in general, if T and S, they are same, if S is equal to T, then what we can write? So this is how we define the powers of a linear transformation. So let me fix this notation here. So when I say T square means what? T composition with itself. So it is actually this T composition with T. So T square means the T composition of T with itself. Or in general, we can talk about any power of T, which is T, so on, T n times. Okay. And just for the convention, we can define T0, the zeroth power of T, as identity operator from V to V if T is not equal to 0. So this is the convention we use, okay, just to make it complete. Okay, so these are just some notations. Now so is it okay so far? Any question here till this point?
No, sir. Yeah.
No, sir.
Okay. So let us define matrix of a linear transformation. Now, when I talk about matrix of a linear transformation, you assume that I'm talking about only finite dimension vector spaces. Okay. So let us understand this first. Suppose that we have a vector space, let's say V, and assume that its dimension is n. So let's say V1 to Vn, this is a basis of, and we have a vector space W, and let's say we have a basis W1 to Wm of W. Let us call this basis B dash. Okay, so these are two bases. And suppose that we have a linear transformation T from V to W. Now this T is a linear transformation from V to W, then we know that every vector in V will have an image. So these basis vectors will also have image. So what does it mean? It means that if I take any basis vector, let's say V1 here, then this T of V1, this will belong to W, and we know a basis for W. So I know that this T of V1, which is an element of W, this can be written as a basis vectors, as a linear combination of these Wi's, basis vectors of W. So let us write this V1, T of V1, as a linear combination of these Wi's. Okay. So let's say T of 1, W1 plus alpha of 2, W2, and so on up to alpha M1, Wm, right? So this is for V1. But similarly, you can do for other vectors also. So for any vector, this T of Vj, you can write it in terms of linear combination of these Wi's. So that means you can find these scalars alpha ij's, such that, so here you can write it in this as a linear combination of these Wi's. Right? This you can do for all j, where these alpha ij, they belongs to the field. Okay. All right. Now, since you have collected these scalars alpha i's, what we can do here, what I will do here, I will form a matrix out of these scalars. So the first column of this matrix would be the coefficients. These coefficients are also called as coordinates of this vector T of V1 with respect to the basis Wi, W1 to Wm. So I will collect these coefficients alpha 1, alpha 2, up to alpha M1, and put them as a column, as a first column of this matrix. So what I'm saying that I will collect these alpha 1 1, alpha 2 1 and so on, the coordinates of T of V1 for with respect to the basis W1 to Wm as the first column of this matrix. So alpha 1 1, alpha 2 1 and so on up to alpha m1. Similarly, I will do for TV2 also and so on. So the jth vector of this matrix would be the coordinates of T of Vj with respect to this basis B dash. So it would be alpha 1j, alpha 2j and so on up to alpha mj. And similarly, the last vector, the coordinates of T of Vm would be alpha 1m, alpha 1n, alpha 2n and so on up to alpha mn. Right? So what would be the size of this matrix? The size would be m cross n. So if V is of size, V is of dimension n, W is of dimension m, then this matrix is of size is of dimension m cross n. Okay, this matrix is called as a matrix of T with respect to the basis B and B dash. So for this we use this notation. This is called the matrix of T with respect to the basis B and B dash. So this is the notation we use. So this is called the matrix of T with respect to basis B and B dash. Okay. So you can also remember it in this way that these scalars. So in each column, so the columns of these are the coordinates of T of Vj. So this is T of Vj, coordinates of T of Vj with respect to the basis B dash. So that means if you multiply these alpha, this column vector with this, let's say W1, W2 and so on up to Wm. So that means when you multiply W1 with alpha 1 1, then W2 with alpha 2 1 and so on up to Wm with alpha m1, and then take their sum, then it will give you T of V1. Similarly, you do for jth vector, it will give you T of Vj. Okay. So this is how we find matrix of a linear transformation with respect to the given basis. Now, if you change the basis here, if you instead of B, B dash, if you change any of these bases, the matrix will also get changed. Right? This is very clear by this definition. How this matrix depends on the basis here. Similarly, if I take any vector, let's say any vector V in V, then I know that this V can be written as a linear combination of basis vectors of V. So the basis is given here, V1 to Vn. So I equal to 1 to n. So the matrix of this vector is denoted by this with respect to B. And what it is just a column vector alpha 1 to alpha n. Okay. So this is a matrix of V with respect to the basis B. All right. So for example, let us take one example first. Let us take this example. You consider this linear transformation P3R2 P2R. So all polynomials of degree less than equal to 3 to all polynomials of degree less than equal to 2. And it is a derivative map which sends every polynomial to its derivative. Now for linear transform for matrix of linear transformation, so this is a linear transformation, this you can verify. We first have to fix two bases, one for domain, one for codomain. So let's say for domain, I will fix this basis 1x, x square, x cube. And for codomain, I will fix this one 1x and x square. then what I need to do in order to find its matrix, I need to see the image of these basis vectors of B, and I have to write the image of basis vectors of B in terms of linear combination of B dash. That's how I'll get the coordinates, the entries of the matrix. So first I will do it for the first vector, which is 1. So what is d of 1? It is just 0. And this 0 I can write in terms of linear combination of B dash. It is 0, 1 plus 0 dot x plus 0 x square. All the coordinates are 0. Similarly, I will do for the next vector. It is d of x is 1 because of the derivative map. So it would be 1, 1 plus 0x plus 0x square. Similarly, you do for other two vectors also. It would be this one, right? And this is for the last vector. Now you have collected all the coordinates, so you can arrange them in the matrix and you can find the matrix of T with respect to B and B dash. Now can you tell me the first column of this matrix?
0 0
0
0
0 0.
0.
Right. And then 1 0 0, then 0 2 0, and then 0 0 3. This is the matrix of size 3 cross 4. This is the matrix of T with respect to B and B dash. Alright. So we can do it for any linear transformation from V to W, and V and W are finite dimension vector spaces. And once but what we have to do for that, we just need to fix two bases, one for domain, one for codomain, and then we can always find the matrix of T. Okay, so let me give you one exercise here so that we can save some time here. I'll put this as an exercise. All right. So it is as follows. Suppose that we have three vector spaces. All are finite dimension. Okay, these are finite dimension vector spaces over the same field. Okay. So assume that T and S, they are linear transformation from V to W. And we have another linear transformation, let's say S tilde from W to Z. Okay. And suppose that we fix basis for these vector spaces, let's say V for V, V dash for W, and let's say V double dash for Z. Okay. For this W also we take the same V dash. Right. So we have fixed basis also for all these vector spaces. Then we know that if I take the sum of these linear transformation T plus S, then I know that the sum is again a linear transformation from V to W. Since T and S both are linear transformation from V to W, their sum is again a linear transformation from V to W. And therefore I can talk about matrix of the sum, right? In fact, you can show that the matrix of the sum is equal to sum of the matrices. So that means the matrix representation of T plus S with respect to B and B dash is equal to matrix of T plus matrix of S with respect to B and B dash, and here also it is B and B dash. Right? Similarly, if you take the scalar multiplication of any linear transformation, it is again a linear transformation, so you can talk about its matrix also, and this is equal to alpha times matrix of T with respect to B dash. Alpha is a scalar. And third one is you know the composition. So the composition map is again a linear transformation. It is a linear transformation from V to Z So what is your expectation here? So what is your guess? Then you see whether that is true or not by proving it. But can you say, by looking at the above these two items, these two results, can you say something about this also?
Product of
यस सर, ये भी स्प्लिट हो जाएगा.
Split हो जाएगा. So what would be the basis? So the matrix of S tilde composition with T, or you can say S tilde
B2
T
B
with
double dash.
B to B double dash. So with respect to the basis B and B double dash is equal to
Yes. Matrix S
S
S
and
tilde B
matrix of
dash.
T.
and
Yes.
S
So
tilde is
B
B
dash
to
to
B double
B
dash.
to
double
B
dash
dash to B double dash and
and
B to B dash.
to B dash.
Right.
yes.
So this is an exercise for you. You can do it. You can verify that this is correct. I can give you some hint how to prove it. This is very easy. For example, let us look at the first one. Suppose that what we have to prove, that matrix of T plus T is equal to the sum of matrix of T and matrix of S. So let's say matrix of T with respect to B and B dash is equal to, let's say, Aij. Okay, this is the matrix, that means the entries of matrix T are represented by these Aij's, and matrix of S with respect to B and B dash is equal to, let's say, this Bij. Okay. Now what you have to do, you have to find matrix of T plus S with respect to B and B dash. So how to find matrix of T? You know how to do that. So what you have to do for this, you have to find the image of the basis vectors. So uh, let's say V is V1 to, let's say, Vn, and B dash is, let's say, W1 to Wm. Okay. Then you have to find these the image of Vi's, the basis B dash under T plus S, and you have to write it in terms of this basis vector B dash. So this T of T plus S Vj, this would be T of Vj, because T plus S is linear. We know we can write it in this way. This is just by definition of T plus S. Now T of Vj, we know what it is. What is T of Vj? Can you tell me?
Linear combination of
Summation over
AIs.
Linear combination
Equal
of V.
to, yes. So this is Aij Wi. Similarly, you can write for this also equal to 1 to I Bij Wi. Right? And then you can write this as I equal to 1 to n Aij plus Bij Wi. But from here you can say that matrix of T plus S with respect to B and B dash is equal to matrix of T plus matrix of S. Can I say this from this equation? Can I say from here that this is
Yes, sir.
true?
Yes, sir. We can say.
Okay, fine. So now, similarly, you can prove the other two things also, other two results also. Let me state one more result related to matrix of T. So this will also be very useful for us in the following lectures. Suppose that we have two vector space of finite dimension for the same field I, and suppose that we have a basis B for V and B dash for W. Okay, and suppose that we have a linear transformation T from, or let's say, V to W. Okay, so this is a linear transformation from, so we have a linear transformation T from V to W. Okay, then you can show that if I take any vector V in V, then T of V is a vector in W, and then if I write T of V, the matrix of T of V with respect to B dash, because T of V is a vector in W and we have a basis for W which is B dash. So this matrix of T of V is actually equal to matrix of T with respect to B and B dash multiplied by matrix of V with respect to B. This is true for all vectors V. Now what this result says? This result says that if you know the matrix of T, then you know everything about the linear transformation. Why this is true? Because then once you know the matrix of T under the given basis, if you know the matrix of T, then you can tell what is the linear transformation, because then you know the coordinates of T of V, because the coordinates of T of V with respect to B dash, if you know these coordinates, then you can always write these T of V using these coordinates, right? So if you know, so using this result, you can say that if you know the matrix of T, then you can actually tell everything about the, or you can explicitly tell what is the linear transformation, because for every vector V, T of V you can write this way. I mean, the coordinates of T of V with respect to B dash you can find. Once you know the coordinates with respect to a basis, you can easily write the vector, right? So this is why this result is important. Let us prove this one. Proof is very straightforward. So what we have to do, we have to prove that for every vector V, T of V, the coordinates of T of V with respect to B dash is equal to this thing here. Okay. So how to start? Can you give me some hints here?
Yes, sir. First we take basis V and basis of V and W. मतलब कि B और B dash को define कर देंगे कि इसमें इतने वेक्टर और इसमें इतने वेक्टर्स हैं.
Okay. Let's say you are saying that let's say V1 to Vn. This is a basis of V, and let's say B dash is W1 to Wn. Okay, fine then.
Now we define a map T to W. So TVI equals to WI. Okay. So TV एक कोई जनरल वेक्टर लेंगे अपन W का, so उसको लीनियर कॉम्बिनेशन ऑफ WI का बता देंगे.
No, so see what you have to prove here. You should not miss the track. So it says that you have to prove that the coordinates of T of V with respect to B dash. Okay, so that means, and this is true for, this should be, you should prove for any vector V. So you start with a vector V in V. Okay, so let us, how to prove this?
तो जो टीवी होगा वो लीनियर कॉम्बिनेशन ऑफ WI मतलब WI होगा ना. सो फर्स्ट वी राइट टीवी इनटू लीनियर कॉम्बिनेशन ऑफ WI. Then
so
we have,
so how, so okay, so let me do what you are saying. Okay, so you take any vector V in V. Now you are saying you write T of V as linear combination of WIs. This is what you are saying?
yes sir.
So we don't know this. So let's say some scalars, let's say AI, WI, right?
Yes sir.
Where AIs belong to F. Then what?
Then this AI forms a vector TV.
So you are saying that this is, yeah, this is matrix representation of T.
Yes
okay,
sir. Then next मतलब लेफ्ट हैंड साइड पहले T का मैट्रिक्स फाइंड करेंगे, उसके बाद T, सॉरी सर अब
so
सर टी का मैट्रिक्स निकाल के और वी का मैट्रिक्स निकाल के
मल्टीप्लाई
कर
that's how you, so the start here is missing. So whatever you said, this is now up to this is fine, but then what? Then you need to you keep in mind what you need to prove. So you always proceed in that direction. So here This is fine that you take a basis of B and B dash. Let's say Vi's form a basis of B and Wi's form a basis. Wi's represent B dash. But then you take any vector V. Now once you have a basis of V and you have a vector in V, then you write this vector in terms of this basis vector. So let's say this V is alpha I Vi I equal to 1 to n. Sorry, I equal to 1 to n. So the basis or the matrix of V with respect to this V would be alpha 1 to alpha n. So this is fine. So we have at least one thing in this expression which we need to prove, right? Here. Okay, all right. Then you assume that the matrix of T with respect to B and B dash is, let's say, Aij, represented by this. Okay. Now what you need to prove? You need to prove that matrix of T of V with respect to B dash. This is what you need to prove. But what we have so far, we have V. So V I can write as alpha I Vi. Nothing special. Then what? Then I can use the linearity of T. I can take this T inside the summation. So it would be, so let me just change this notation here. Let's say alpha j Vj, j equal to 1 to n. Okay. Then you take T inside. So it means j equal to 1 to n alpha j T of Vj. Again fine. Now what? Can you tell me the next step?
सर टी ऑफ वीजे को लिख देंगे.
T of Vj को लिख देंगे कैसे? T of Vj को कैसे लिखेंगे?
सर WJ.
In terms
सर
of
W की form.
A1j, A2j, A3j.
right. So in terms of these coordinates or the entries of this matrix, so you write this T of Vj for every j. So it would be I equal to 1 to m Aij Wi. This is because we know the matrix of T and it is represented by Aij. So we know these scalars. Now you can write the same thing here. You can take the summation with index I outside. So there is nothing special here. You can check that this is not going to change anything. So I'll rewrite this thing. I'll take the summation with I outside. So it would be j equal to 1 to n Aij alpha j and then Wi. You can verify that these two things are same. But are you done with this? Can you say something from this now? Now, can you tell me what would be the so we have written T of V in terms of as a linear combination of these Wi's. So that means we know matrix of T of V with respect to B dash. What it is? If you look at these, what would be the first element? It would be j equal to 1 to n A1j alpha j. And similarly, you can write for others also. The last element would be j equal to 1 to n AMJ alpha j, right? But what it
Yes,
is?
sir.
Now, can you tell me what is this? Is it not equal to this one?
Yes, sir.
Right? So, and that's
Yes, sir.
you are done. So see that if you start with in the proper way, if you start the proof, then you almost like you know how to prove that. So the start of the proof is very important. How to start? Whatever result you prove, you first think about it, and then you take a start. If your start is right, then you can half of the job is done. then you just have to follow some argument which you know from your basic study. Okay, so let me make some observation here. What we have done, let me summarize what we have done. So I will write these things as observation, because at the end I will conclude something. So let me make this observation first. What we did, if we have a linear transformation, then we can always find its matrix representation. So from linear transformation, we have a matrix, right? So if we have two vector space V and W, once we fix the basis, we can always find for every linear transformation, we can always find its matrix representation. So from linear transformation to to matrix, this way we have already seen. All right. Now I want to show that if suppose we have a matrix, then also we can like find a linear transformation in some way. For example, let us start with this easy observation. So suppose that we have a matrix. So we have a matrix, let's say A, over the field F of size M cross N. Okay. Now, can you tell me? So let me ask in this way. So this is a matrix of size M cross N. Now, can I define a linear transformation from, let's say, Fn to Fm such that the matrix of T with respect to, so you have to give me two bases, for one for Fn, one for Fm, such that the matrix of T is actually equal to A. So you understand what I'm saying? So I have a matrix A here of size M cross N over the field F. Now I want to say that I can always find two bases B, one for B, one for Fn. So let's say B here and B dash here, such that matrix of T with respect to B and B dash is actually the given matrix A.
Yes, sir, we can find.
So you tell me the basis first, and then the linear transformation. So what would be the basis here?
Standard basis.
Standard basis. So if you take standard basis for Fn and also for Fm, so let's say these are standard basis, both for Fn and Fm. And then you have to tell me the map also. You take
So
the standard basis.
First we define A equals to Aij.
Yeah, A equal to Aij, that's fine. Then so you are trying to define a map from Fn to Fm such that the matrix of T with respect to B and B dash is equal to A. This is what you are trying to do. So you tell me what it would be. So if I take any vector here in Fn, then T of X would be in Fn.
AX.
If I do it Ax, then you can verify that the matrix of T with respect to B and B dash is equal to A. So this is linear clearly, and the matrix of T with respect to B and B dash is equal to A. So this is easy to observe. Instead of taking a standard basis, now the question remains same. Question remains same, but now instead of Fn and Fm, I will take any vector space, let's say V of dimension n and W of dimension m. So the question is now, so the modified question, or let's say the second observation is the following. Suppose the same thing, we have a matrix A of dimension of size m cross n over the field F. Let's say the entries of A are denoted by Aij. Okay. And then we have two vector space, one is V and one is W. Both are finite dimension vector spaces over the same field F. Okay. Assume that the dimension of V is n and dimension of W is m. Okay, and assume, let's say, a basis V1 to Vn of V and W1 to Wn of W. Okay, now the question is, can you find a linear transformation T? So the question is, can you find T from V to W such that the matrix of T with respect to B and B dash is equal to A? This is the question. So it is actually the same question, but in general, instead of Fn and Fm, I have replaced V and W. Instead of standard basis, I have taken any two bases. Now the question is same. Can you still do that? And the answer?
So T of V equal to
Take a
T of V equal to
T of V equal to
A dot matrix of coordinate of V with respect to B.
A dot matrix of V with respect to B.
With respect to
Then, but this is not an element in W. W is, you don't know whether, so here this way it would be a column vector. This is a column vector, right? But elements of W may not be of this form. Just need to do some more, something more.
Sir, TVJ is equal to summation Aij I from 1 to n Wi.
That won't give you the thing. Because of similar things. So here you have like guessed almost correct thing. The only thing is that the right hand side here is not an element of W. So for that you need to do something. If it is not a element of W, you have a column A multiplication with this vector here, matrix of V. This is a column vector here. So can you use the entries of this column vector and make a vector in W? Can you like, if you have these m coordinates or m coefficients here or m scalars, using them can you make a vector in W?
सर summation Aij Wi तो W में ही होगा ना?
तो Aij Wi नहीं बोल रहा मैं, यहाँ से देखो, this is a vector, this A is a matrix, this is a vector, so this multiplication it would be a vector. Now this vector, this is a vector, but the elements of W may not be of this form. Now can you use this entries of this vector to make a vector in W?
सर होल इस मतलब इसको बी डैश के फॉर्म में लिख सकते हैं, मतलब कि पूरे पर बड़ा ब्रैकेट और बी डैश ऐसा कर सकते हैं
इसको let's say ये entries है alpha 1 to alpha m. Can you right now use these alpha i's to make a vector in W?
सर अगर इसको मल्टीप्लाई कर दें b ऑफ w ऑफ v डैश से,
So अगर आप ऐसा कुछ कर दो तो then this is definitely a vector in W because it's a linear combination of these two vectors. And then you can think of like this kind of map. So what I'm saying is that this idea will work, but you have to make sure that your map is well defined. So the question is, you can always do. So the answer is you can always define a map T from V to W, and it would be this one. So define T from V to W such that you take any vector V which you can write in this way, alpha j vj, and then you send it to this one, I equal to 1 to m, j equal to 1 to n, aij alpha j wi. then you can verify that this T is a linear transformation from V to W, such that the matrix of T with respect to B and B dash is right. So whatever be your vector space V and W, once you have two bases B and B dash, then there is a way to define linear transformation from V to W such that the matrix of T is actually, with respect to these two bases, is actually the given matrix, right? So now you know that from a linear transformation you can find a matrix, and if you are given a matrix, you can always find the linear transformation matrix of which with respect to some basis is the given matrix. So both ways you know now. So let me define now. I'll use this in the next definition. So it is isomorphism. What is isomorphism? So if suppose we have two vector space V and W over the field F, then and T is a linear transformation from V to W. It is a linear transformation. Then this T is called an isomorphism if T is linear. So T is already linear. So then this is called isomorphism if T is 1, 1 and on T is 1, 1 and on. So a bijection, a linear bijection from a vector space V to W is called an isomorphism. And if this is the case, then V and W are called isomorphic. So V and W are called isomorphic if there is an isomorphism from V to W. Okay. So with this we can stop. So we still have 2 minutes. So I can briefly mention this result, that if you have a so let me write it in general way. So every n dimensional vector space over F is isomorphic to Fn. Every n dimensional vector space over F is isomorphic to Fn. Now if you want to show, so if you want to prove this, then how would you do that? Can you quickly tell me the idea here?
Yes, sir. By taking a basis of vector space, every element of V can be expressed as the linear combinations of basis vectors. Then by taking the coordinates vectors, coordinates.
Yes, yes, I understand. So what she's saying is that you take, suppose that this is a vector space, and sorry, suppose this is V and dimension of V is n. Then what you do, you take a basis, let's say B of V. This is a basis. Then you define this linear transformation T from V to Fn. How it is defined? You send this n V to matrix of V with respect to V. So this is a linear transformation, and this is actually an isomorphism, and therefore every n-dimensional vector space is isomorphic to F. So we'll continue obtaining result on this isomorphism in the next class. So just to remind you that the first quiz is scheduled on Friday at 6 p.m. It would be via Gradescope. So yeah, all the best for that. So we stop
Sir,
here.
sir,
Yes.
sir, means I was having a request, sir. Since there at some moment there is internet problem, then I will try my best to upload in Gradescope. If it is not possible, then I can send via mail.
So that's
Yes, sir.
I said you try to make sure that you don't have any internet issue. you try to make sure that there is no internet issue. Try to change your network, because see, this is not only for this quiz or this course. There would be several other exams also for you. And if you make the same thing for all the exams, then it would be difficult. So you make sure that there is no connectivity issue, there is no technical fault at your end, so that you can finish your exam and you can upload your answers on Gradescope on time. Okay.
Sir, means that we will try our best. Means whatever the chances we are having, we will try to minimize that, sir, and we will mistake all the action. But sir, at some moment there is a complete means we are not able to upload, or it is not uploading file on the given platform, sir, Gradescope.
But then there is no other option. Then you have to miss the quiz, or you have to reappear for the quiz. There is no other chance, because if there is no network at your end or no connectivity issue, and if there is a connectivity issue, then you won't be able to upload, right? And then how would I know that there is no authenticity at your end and from your side, that this is your answers, or you have not copied it, or you have not taken it from other. It won't be the case, or it may not be the case, but there is no guarantee. How would I make sure that? How would I ensure that there is um, no cheating at your end? It's not only for you. It's like for all of you, like all those who are going to appear for exam.
Okay, sir.
So you have to reappear for the exam. You make sure you try to make sure that there is no connectivity issue, there is no technical fault during the exam, and then you try to. It's uploading on Gradescope is much more easier than sending on email, because on Gradescope you can just take the photo and then you can just upload your JPG file also. So it is much faster on Gradescope. This is my experience. You can also experience that by doing by uploading on the demo examination. So it is much more easy. So we can stop now.
Sir.
Is there anything else? Yeah.
Sir, I have a doubt on proving ZP is a field. So multiplicative inverse in general find कैसे करें?
So you can ask this during the tutorial, because it's already 9:30 and most of you are having other class, or you can stay and the others may leave.
Okay, sir. Sir, we have no classes now.
You have no class now? Yeah. So ZP is a field. Are you sure? Is it? You are convinced that ZP is a field when P is prime?
Sir, yes, sir.
Okay. So now, if you know that it is a field, then it should satisfy all the properties of field.
Yes, sir.
So it will have a multiplicative inverse.
Yes, sir. But how to find it in general? That's my problem. So I am proving that ZP is a field. I satisfied all the properties, but in multiplicative inverse, I feel difficulties.
So if let's say you have a non-zero element in ZP, okay?
Yes, sir.
Then you have to. So it's like this thing. So let me do it here. So if you have a non-zero element in ZP, then for this you have to find X, which is actually the multiplicative inverse, such that AX equal to 1, right? Where 1 is the unity element.
Yes, sir.
Right?
Yes,
so
sir.
how would you do that? How would you? Is it possible? First, you tell me. Is it possible? It's possible because it's a field, you are saying. So what you do here, you just find the how do you do that? So you find, let's say, X. So you can do it in this way. So since P is prime, A is an element of this, that means GCD, the greatest common divisor of A and P is equal to 1. Right? Because P is
Yes.
prime and A is an. Now,
Yes.
from here, you can say that there exists, this is 1, so there exists X such that AX is equal to 1 mod P. You just use this modulo operation and you will find this. Just think about it. This is very straightforward. I mean, you just use this modulo operation.
Sir, how I can write A in terms of X?
A, you don't have
In
to
terms
write
of
A in terms of X. See, you need to find, for multiplicative inverse, you need to find X. Right?
Yes, sir.
This X will depend on A, but you don't exactly have to write it in terms of A. You just need to find X that satisfy this condition here. Now this X you can find this way, because GCD of A and P is equal to 1. So this implies that you can always find X such that X modulo X is equal to 1 modulo P. So this X is actually, so this is a candidate for the inverse. So if suppose you can find this X, then this is a candidate for the inverse. And since you can verify that this is a unique X, so it is the inverse. So this is how you can find. You take an example, let's say P equal to 3 or 5.
Yes, sir.
And
एग्जाम्पल से हो रहा है. Yes,
so
sir.
in general, you see, if you don't know the P, what is P here? What is your element? You don't know. Then in general, how would you say? In general, you would say in this way only, na? Take, since GCD of A and P is equal to 1, then this implies that there exists X, and this X. So now if you put P, value of P and value of A, then you will be able to find X. In general, तो
Yes.
ऐसे ही लिखोगे. If you want to say for a particular example, then only so for that you give value to A and value to P also, and then you apply this result and find X. This is how you do. But
Yes, sir.
if you
Then
want to say in general तो ऐसे ही लिखोगे.
yes, sir.
So if
Then
you want to verify,
we
yeah.
can write that for each x bar belongs to ZP. We can find x inverse
So
bar
this,
such that ऐसे लिख सकते हैं मतलब.
so you want to write it like in some particular form. So I
Yes, sir.
did not get your point. So
सर जैसे फील्ड प्रूफ करने के लिए हम 1 to 11 ऑल प्रॉपर्टी सेटिस्फाई करते हैं तो इनवर्स मल्टीप्लिकेटिव इनवर्स में कैसे
okay,
लिखे ये.
okay. So you want to write it in like in that way.
Yes, sir.
Okay. So let me think about it. But this way is fine. You can find this X and then you can do. So that is fine.
So this x will be equal to A inverse, but we are not sure that the x belongs to ZP. X may not belong to
X
ZP.
X may not belong to.
ZP.
No, so here if there exists such a X in ZP such that
So
AX equal to 1. So
we have to show that the x belongs to ZP. We will take the help of division algorithm for this.
yes, exactly. So that's how this existence of such a X is involved. But she
Yes.
wants to write X explicitly in terms of like A inverse. So that's what I now I understand what she means. So just a minute, huh? Let me think if
Okay, sir.
So there is a way. I remember that there is a way to write this in terms of this. But anyway, so I, I can tell you in the maybe in the next class or in today's tutorial. Is it okay?
Okay, sir. Okay, sir. It's
Yeah, I
fine.
have to recall this. I don't remember right now, but I will recall and I will tell you in the tutorial.
Okay, sir.
Hopefully, I think there is a way to write this. Okay.
Okay, sir.
सर
Thank you.
सर जो
Yes.
पेज को पे हमने अपलोड करना है वो पीडीएफ ही करना है या सिर्फ इमेजेस भी क्लिक करके अपलोड कर सकते हैं?
You can upload images also. So while uploading, you might have seen that you
Yes, sir,
can
there are
try
two
that.
options. Yeah.
Yeah, there are two options. One is upload a picture and upload a PDF. So you can upload pictures also, but you try this first.
Okay, sir.
You try uploading a picture. If it is faster, then it's fine.
Okay, sir.
Okay, and please try to assign pages to every question. So that way, like it would be like convenient for us also. Otherwise, it may happen that if you don't assign a question to each page, then some of your question might be like unchecked. So we can skip or we can like miss some of your pages which are assigned to a particular question, because there would be many pages you will be uploading and it would be difficult for us to do. All right, so we can stop here now. If there is any other question, you can ask.